Hello and welcome back to Physical Geology. I am Robert Lopez. Today I want to cover the prelude to our textbook, Essentials of Geology here. And I do have a quiz on this that's due on Saturday. You can see that this section is titled, And Just What is Geology? I've actually made a PowerPoint presentation on this so we can take a look at it this way. So one thing to think about is, and what is geology? So what we'll see is, it's to see to see how the world was made, right? How did it come to be? And you'll find that in chapter 1, we'll talk about the Big Bang and the solar nebula. But here we just want to make some points in how Earth has changed through time and will continue to change through time. Geologists are actively in search of resources, right? Our society depends on resources. We're concerned with our water quality, the soil, right? So geologists are involved in that investigation. And then obviously geologic hazards, right? There's earthquakes, flooding, landslides, volcanoes. All those are practical matters that affect society, right? Now, as we keep going along here, when reports begin, news reports begin with saying something like scientists say, well, we know they're talking about geologists, right? Because there are earthquakes involved, landslides, volcanoes, toxic chemicals coming from a waste dump or from a landfill somewhere. Where is that stuff going? Geologists can trace those materials, right? Flood insurance is very expensive. Well, geologists make flood hazard maps, right? How long will our oil last? What's the differences between reserves and resources, right? So those are things that geologists are concerned with. I always say, or at least what my professors told me when I was in college, is if it's not grown, it's mined. It's taken from the earth, right? And that's our society today. Now, as we keep going here, you'll see that geology is a practical subject. It identifies those regions of geologic hazards. It assesses the supply of fossil fuels and the price of fossil fuels. In fact, the price of a barrel of oil has really fluctuated in the last few years. A couple of years ago, it was at $120 a barrel. Earlier this year, in 2016, it was at about $30 a barrel. Now it's about $50 a barrel. So that's changing based on the supply and the accessibility of these resources. Now, as we keep going, we'll see that another theme of this book is that Earth is going to be divided into these systems that influence each other, that are interconnected. And so there's the atmosphere, the geosphere, which is a solid Earth, the crust, mantle, core. So mostly in this class, we'll be dealing with that geosphere, but it's affected by how glaciers, the cryosphere, how it moves across the land surface. By the hydrosphere, how erosion from rivers or ocean waves affect the geosphere. And by life itself, how fossil life can be traced in the rock record, right? So in terms of physical science, minerals, rocks, surface processes, they allow us to see natural laws in action. You think of a landslide, that's gravity working there. The flow of water, that's gravity. The radiation of heat from a lava flow, the spinning of whirlpools, magnetism, all those are natural laws that govern our universe, and we can observe those through geology. Another big part of this textbook is plate tectonics. It's the overarching theory in geology, and it explains so much of what we see. Again, Earth has an origin, and it really originates from the solar nebula. So in chapter 1, I'll talk more about this and how this comes to be here. But Earth formed like the other planets from this solar nebula, and it orbits the sun in the same direction as all the other planets do on this disk called the ecliptic. Earth is very old. 4.57 GA. You'll see that I'll use the suffix here, GA, for giga years, and that's 1 times 10 to the 9, so that's a billion. So Earth is 4.57 billion years. And the face of Earth has changed many times through plate tectonics. And how do we know this age? Well, many of the rocks that formed in the early Earth, well, the early Earth was too hot to form rocks. And so the oldest rocks are about, they're about just a little over 4 billion years old. And by that time, Earth got cold enough, and also Earth experienced an early history of very intense meteor bombardments. So any rocks that might have formed or any crust that may have formed was probably obliterated by these deep impacts of asteroids and meteorites. But by about 4 billion years ago, we find that rocks started to form because Earth started to cool enough to form them, and there are fewer meteor impacts. So the age for 4.57 we have to get from asteroids and meteorites that are still out there and that fall on Earth. And you can see that later on. I'll talk about this curve and how we get the age of the Earth here, right? Now, as we keep going, there's these internal processes and external processes that drive weather and climate and plate tectonics, right? So the internal heat engine, well, that's radioactivity, and it drives plate tectonics, right? It's causing mantle convection, maybe flow in the asthenosphere, certainly volcanic eruptions. So that's the internal heat engine, movement of tectonic plates. Whereas the external heat engine, that's coming from the sun, right? And so that's given us our weather patterns, our climate, which leads to erosion. Now, as we go along here, geologic phenomena affects our environment. So society is really dependent on geology, right? So here's just one example. As the planet warms up, our glaciers are going to melt, and which is going to cause sea levels to rise. So here's a prediction that by the year 2100, we may see up to a 6.6 foot rise in sea level. And you can see that in terms of populations, there's 7.8 million people living in these regions that have to be displaced, right? So obviously this number will increase as our populations grow as well. Another aspect of this book is there is this, well, here's where I talk about those chemical systems, right? The nutrient cycle from one reservoir, the hydrosphere, to the geosphere, to the biosphere, right? So there's a whole cycling of nutrients from minerals and rocks to living organisms. Science is about observations, and people make those observations. So here's another observation that Eratosthenes made. He's a Greek librarian in Alexandria, actually, in the first library there. Yes, Eratosthenes calculated the diameter of Earth by making observations of how the sun on the shortest day of the year, which is the solstice, the summer solstice, he would find that the sun hit water in a well, right? Directly, the sunlight shone on the water. And so he knew that the sun was directly overhead of that position. But then he knew that on that same day, the sun made a shadow from a post here, right? So what would happen is that because there was a shadow in Alexandria and the sun was directly overhead in Syene, he could calculate basically the diameter of the Earth. So again, these are from observation. The way they did it, they made models. They try to use math and laws and experiments to explain the phenomena that they saw. And so one thing they really tried to focus on was not using supernatural powers. He knew that there had to be some method to this, and a good way to do it were debates and these models. Now these next couple of sections deal with some boxes that are in your text here. So P1 for Prelude 1 is a box that talks about heat transfer. And so remember, kinetic energy is a vibration of molecules, and the faster they vibrate, the warmer it will be, which means more thermal energy. The slower, there's less thermal energy. And so we have to have a standard for temperature. And so obviously 0 degrees Celsius is the temperature where water freezes, whereas it boils is at 100 degrees Celsius, right? And in some of the problems, you may be asked to convert between degrees Celsius and degrees Fahrenheit. And then this term absolute zero is the temperature where where basically matter can get no colder. That's the absolute coldest matter can get, and that's the temperature at which all kinetic energy ceases. It stops. It goes to zero, right? And so that's going to be this 0 degree Kelvin, which is negative, I don't have it in here, but this is negative 273.15 degrees centigrade, right? So that's going to be the absolute zero. Now, as we go along here, remember, temperature is how fast the molecules vibrate, but heat is how fast and how many. So heat is really a measure of energy, and we usually measure heat in calories, right? But in this case, when we look at heat that's being transferred, we can transfer it as radiation. So let's think of this heat coming from the sun or this fire. You feel the heat in waves. Or heat can move in this convection, which are these circular currents. And the key thing is that the atoms are moving. So the atoms are moving in convection. Molecules are moving here. But conduction here, because the pot is getting hot, the atoms are starting to vibrate faster in different parts of this handle, and eventually the handle gets hot just because the pot is hot, right? So there are no atoms being transferred here, only heat is being transferred. So the only one that's really seeing atoms transfer is this convection, right? The movement from hotter to colder regions. Finally, this last one, advection, is when you inject a hot fluid into a porous membrane where there could be cracks or pores. So like, for example, magma injecting into country rock, into surrounding rock. So it'll heat up that adjacent rock. And that's kind of a form of conduction as well. Now, as we look over here, this part about scientific method, you know, we follow a systematic approach to solve these scientific problems. We have to recognize what the problem is, make some observations, some visual ones, and the more important ones are these quantitative ones, which are numbers. We come up with hypotheses. We try to explain the phenomena that we observed, and then we have to test them. We run experiments, right? And you'll see in lab 1, we'll talk about variables. There's dependent variables and independent variables, right? So we want to vary the independent variable and see what happens to that dependent variable, right? And then that can help us solve the problem. And then finally, scientific theories make predictions that are testable, repeatable, and they're supported by an abundance of evidence. All right, we'll come back to this as we go along.